Hi, I'm Rafael Roberto from Voxel Labs in Brazil, and I'm going to talk about semantic modeling. And this work was developed in partnership with Kyushu University in Japan and Technical University of Graz in Austria. And finding high-level semantic information from point clouds is a challenging task, but have a lot of applications. For instance, we can use the semantic information to help us navigate in an environment or improve the representation of objects. And this task is even challenger when we are dealing with sparse point clouds. And we found an urge to develop a high precision semantic technique to find primitives on sparse point clouds. Sorry. Okay. Our method uses the generate process of a slump system to evaluate the precision of the detected primitives. So on each keyframe of the slump system, the slump system updates the map and refines the point cloud. At this point, we run efficient ransack to extract primitives, basic primitives from the scene. However, due to the sparse point and to the noise, efficient ransack finds some frequently outputs inaccurate primitives. In order to solve this, we first fuse different shapes that belong to the same object to improve the representability and the reliability of this point cloud. And after that, we look at the 3D bound box of the primitives and also the distance of the center of Mars to match primitives in the current keyframes with the one detected previously. So with that, after that, we can also evaluate the type of the primitive that was detected in the current keyframe and to evaluate if it matches with the objects that was found previously. With that, we can replace incorrect detections by the correct one. We can also recover objects that was not found in the current keyframe but was there in previous detections. After this, we compute the reliability of the shapes. And let's take the globe example of last slide. And here we can see that this globe was detected 3 times as a sphere and 1 time it was detected incorrectly as a cylinder. And we can use a geometric evaluation. So we measure the average distance of the input points to the primitive. And for correct detections, the average distance is much slower, is fewer than the incorrect ones. And we use the distance to compute a weight for each detection. And based on that weight, we can see that the probability we have of this globe be a sphere is 10 times higher than a cylinder. But sometimes this weight is not enough to detect the primitives. And when this happens, we run statistical evaluations. And basically, we look the history of the detection, and we see if this history of detection is random or not. Only non-random detections are considered reliable. In our tests, we could see that we could improve the precision and stability of existing method in 28%. And we can also reduce the memory consumption in 9 times. So I invite you to discuss the results and more details about this work in the poster sections. Thank you.